Hello everyone, I am Bireshwar Roy. I am currently pursuing my fourth year PhD in the Department of Physics, Indian Institute of Science, Bangalore. I am working in the field of experimental condensed matter physics. In this video, I will be discussing all the questions from the topic electromagnetism appeared in the exam GATE Physics 2020. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark. The topic of the question is electromagnetic theory. The question is a medium with relative permittivity or dielectric constant epsilon r greater than 1, relative permeability mu r equals to 1 and conductivity sigma greater than 0 is semi-transparent to an electromagnetic wave when option A, conduction current is very greater than displacement current. Option B, conduction current is very less than displacement current. Option C, conduction current equals to displacement current. And the last option, option D, both conduction current and displacement current are 0. So let us see how to solve this problem. For a linear, homogeneous and isotropic conducting media, the Maxwell's equation can be written as curl of H vector equals to JC vector plus JD vector. So this is also known as modified Ampere's law. In this equation, the H vector is the magnetic field intensity vector, JC vector is the conduction current density, and JD vector is the displacement current density. Now, the conduction current density JC vector is given by sigma times E vector. Here sigma is the conductivity of the media and E vector is the electric field vector. And the displacement current density JD vector is given by del D del T. Here D vector is the displacement vector. Now this is also given by epsilon times del E del T. Here epsilon is the permittivity of that medium. Now if we consider a plane wave or monochromatic wave solution for the electric field, then it can be written as E vector as a function of r vector comma time, that is t, equals to E naught vector times e to the power I k dot r minus omega t. Here E naught is the amplitude of the electric field and k vector is the wave vector for that electric field. Now the conduction current density Jc is given by sigma times E vector. Now we'll put this E vector expression in this equation. So we'll get Jc vector equals to sigma times E naught vector times exponential of I times k dot r minus omega t. And the displacement current density vector will be given by epsilon times del E del t. So we'll put the expression for E vector in these partial derivatives and we'll get epsilon times minus I omega times E naught vector times exponential of I k dot r minus omega t. Now E naught vector times exponential of I k dot r minus omega t is our actual electric field vector. So we can write it as JD vector equals to minus I omega times epsilon E vector. Now we'll take the ratio of the magnitude of the conduction current density vector, that is JC vector, and the displacement current density vector, that is JD vector. So it can be written as mod of JC vector divided by mod of JD vector equals to mod of sigma E vector divided by mod of minus I omega epsilon E vector. So we'll get effectively sigma by omega epsilon. Now as we are given the medium as semi-transparent medium, for that we have the condition that sigma by omega epsilon is very less than 1. This actually implies that the medium is the poor conductor or lossy dielectric. Now, if we implement this condition in the expression of the ratio of Jc vector and Jd vector, then we will get mod of Jc vector divided by mod of Jd vector equals to sigma by omega epsilon, which is very less than 1. So, this implies that mod of Jc vector is very less than mod of Jd vector. So, we can conclude conduction current for in this media is very less than displacement current, which is option B is given in the question. So, according to our solution, a medium is semi-transparent to an electromagnetic wave when the answer is option B, that is conduction current is very less than displacement current. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark and the topic of the question is electromagnetic theory. The question is, if E vector and B vector are the electric and magnetic fields respectively, then E dot B is option A, odd under parity and even under time reversal, option B, even under parity and odd under time reversal, option C, odd under parity and odd under time reversal, and the last option, option D, even under parity and even under time reversal. So let us see how to solve this problem. So E vector is the electric field vector, that is polar vector. So polar vector is related to the direction of motion of a system, that is translational motion, and that has a particular starting point. But magnetic field vector B vector is an axial vector or pseudo vector. So what is the axial vector? It is related to the direction of rotation of body. It doesn't have any starting point, only it has a direction along an axis. Now we will be talking about the parity operation and time reversal operation. First, starting with the parity operation. Parity operation or the transformation is the space inversion or reflection. It means flip in the sign of spatial coordinates. So if we consider p cap as a parity operator, so it will turn the position vector r vector into minus r vector. So it will flip the sign. Now we will be talking about time reversal operation. It means the operation of replacing the time with its negative value. That means t will become minus t. So that it indicates an phenomena in which time runs in backward direction or all the motions are reversed now. So if t cap is the time reversal operator, so it will give minus t upon acting on the time. Now consider a particle of charge q moving with a velocity v in an electric field E vector and magnetic field B vector experiences a Lorentzian force that is given by this expression, force F vector equals to q times the electric field vector E plus v cross B. Now force can be written as mass of the particle times acceleration, and acceleration is d2r dt2. Now if we replace the r vector, that is position vector, by minus r vector, then the force will be m times d2 of minus r dt2, and that will give minus of m d2r dt2. So this will be basically minus of force vector. Now if we replace the time by minus t, then force vector will be m times d2r d of minus t square. So this will be m d2r dt2, and that is same as the force vector, that is F vector. So what we have learned, if we operate the parity operator on the force vector, so that means force vector will flip its sign under space inversion. or deflection. So this will become minus of F. But under time reversal operation, the force vector doesn't change its sign. Now coming to the Lorentz force, that is F vector equals to Q times E plus V cross B. Now charge doesn't change its sign under parity operation as well as time reversal operation. So in this force there are two parts, one is electrical force, one is magnetic force. So we will denote it by 1 and 2. Under parity operation, F will change sign, that we know already. So from that information, in this part 1, the E will flip its sign because F is changing its sign under parity operation. So E will obviously change its sign. In 2, Q into V cross B will flip its sign under parity operation. Now V, that is velocity, is dr dt. Under parity operation, V will change its sign, that is minus V, because R is replaced by minus R here. Now under time reversal operation, the velocity will also change its sign, so it will become minus V. Now in 2, the term Q into V cross B, under parity operation, it will change its sign because force will change its sign. That means it will also change its sign, this term. It means the magnetic field vector will remain unchanged because velocity is changing its sign. So that will give the negative sign here. So B has to be invariant under parity operation. So what we have learned till now, under parity operation, the electric field vector changes its sign. So it is odd under parity operation, but magnetic field vector doesn't change its sign under parity operation. So it is even under parity operation. Under time reversal operation, the force vector doesn't change its sign, but the velocity vector changes its sign. So it will turn into minus V under time reversal operation. So this suggests that the electric field vector E will not change its sign under time reversal operation, but the magnetic field vector will change its sign under time reversal. So magnetic field vector will change its sign because here V is also changing its sign under time reversal operation, and magnetic field also changes its sign under time reversal operation, and both this cross product will become positive under time reversal operation. That means force will not change its sign. So what we have learned, electric field vector doesn't change its sign under time reversal operation, so it is even under time reversal operation, but magnetic field vector changes its sign under time reversal operation, so it is known as odd under time reversal operation. So in a summary, what we have, under parity operation, E, that is electric field vector, flips its sign, so it will become minus E vector, but under time reversal operation, it doesn't change its sign. In the case of magnetic field vector doesn't change its sign under parity operation, but under time reversal operation, it changes its sign. Now coming to the main part, that is the dot product with electric field vector E and magnetic field vector P. Under parity operation, on this E dot B, that quantity, it will give minus E dot product with B, because parity operation will give minus E, but B will remain the same. Effectively, under parity operation, the quantity E dot B will become minus E dot B. So this is odd under parity operation. Now we will operate the time reversal operator on this quantity E dot B. The time reversal operation will give E as E vector, so E will not change here, but B vector will flip its sign, so it will become minus B vector. Effectively, we will get minus E dot B. So under time reversal operation, it is also odd under this operation. So effectively, what we are getting, under parity operation, E dot B will become minus E dot B, that is odd under parity operation. And under time reversal operation, this quantity E dot B will become also minus E dot B. So it is odd under time reversal operation as well. So according to our solution, the E dot B is odd under parity and odd under time reversal. So our option C is the correct option for this question. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 1 mark. The topic of the question is electromagnetic theory. The question is, far from the Earth's magnetic field can be approximated as due to a bar magnet of magnetic pole strength 4 into 10 to the power 14 ampere meter. Assume this magnetic field is generated by a current carrying loop encircling the magnetic equator. The current required to do so is about 4 into 10 to the power n ampere, where n is an integer. So the value of the n is, so we have to find the value of n here. One information is given in this question is Earth's circumference is 4 into 10 to the power 7 meter. Now let us see how to solve this problem. Far from the Earth's magnetic field can be approximated as due to a bar magnet of magnetic pole strength P equals to 4 times 10 to the power 14 ampere meter. Now we can assume that this Earth's magnetic field is generated by a current carrying loop encircling the Earth's magnetic equator. So the current carrying loop has the radius A, which is the radius of Earth, and the magnetic dipole is directing towards the north direction. The magnetic dipole moment is mu, and the length of the magnetic dipole is 2a. So magnetic dipole moment mu vector of the bar magnet of Earth is given by mu equals to p times 2a. So this is the relation between the magnetic dipole moment with the magnetic pole strength. Here a is the radius of Earth. Now assume that this magnetic field is generated by a current carrying loop encircling the magnetic equator. So in the diagram we can see there is a current carrying loop encircling the magnetic equator of the Earth having radius small a, which is the Earth's radius, and the passing current is I, and due to this current magnetic field will be generated and the corresponding magnetic dipole moment is mu vector, which is directing towards the north direction. The current required to do so is about 4 into 10 to the power n ampere, that is given in the question. So our current I equals to 4 into 10 to the power n ampere. We have to basically find this n value. Now we know magnetic dipole moment due to a current carrying loop having radius small a is given by mu equals to I times pi a square. Now we'll compare the equation 1 and equation 2. So equation 1 was magnetic dipole moment is equals to P times 2a, where P is the magnetic pole strength, and also for the current carrying loop the magnetic dipole moment is I times pi a square. So we'll equate that two equations. So we'll get P multiplied with 2a equals to I times pi a square. So from here we can get I equals to P times 2a divided by pi a square. So this will give I equals to 2p divided by pi a. Now in the question it is given that the magnetic pole strength P equals to 4 times 10 to the power 14 ampere meter. The current is 4 into 10 to the power n. Earth's circumference, that is 2 pi a, is 4 times 10 to the power 7 meter. So we'll use this information in this equation. So we'll get 4 into 10 to the power n equals to 2 times 4 times 10 to the power 14 divided by 2 times 10 to the power 7. So here 2 and 2 will be cancelled out from the numerator and denominator, and from the left side and right hand side the 4 will be cancelled out. So effectively we will get 10 to the power n equals to 10 to the power 7. So the value of n is 7 for this question. We can also solve this problem in an alternative manner. The definition of the pole strength is given by P equals to surface integral of H vector dot ds vector. So we are considering the Earth's magnetic field is due to a current carrying loop having radius small a. So for that current carrying loop, the H field is given by I by 2a along the z cap direction. So here it will be along the north direction. So from the definition of pole strength, we can write P equals to H times area of the loop, that is I by 2a times pi a square. So it will give the pole strength P equals to I times pi a divided by 2. We can write it as I by 4 times 2 pi a. So here 2 pi a is the circumference of the Earth. So we'll put the value of P here, that is 4 into 10 to the power 14, and I value is given in the question 4 into 10 to the power n divided by 4 times 2 pi a, that is circumference of the Earth, that is 4 times 10 to the power 7. So if we just cancel out the 4 and 4 from the left hand side and right hand side, and from the numerator denominator the 4 will be cancelled out. So effectively we will get 10 to the power n equals to 10 to the power 7. So by comparing we can get n equals to 7. We solved this problem using two different methods, and from the solution we found that the current required to do so is about 4 into 10 to the power 7 ampere, where n is the integer. So our n value is 7 for this question. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 1 mark. The topic of the question is electromagnetic theory. The question is, a conducting sphere of radius 1 meter is placed in air. The maximum number of electrons that can be put on the sphere to avoid electrical breakdown is about 7 times 10 to the power n, where n is an integer. The value of n is, so basically we have to find the value of integer n. In this question we have to assume breakdown electric field strength in air is mod of E vector equals to 3 times 10 to the power 6 volt per meter. Permittivity of free space is epsilon naught equals to 8.85 times 10 to the power minus 12 farad per meter, and electronic charge E equals to 1.6 times 10 to the power minus 19 coulomb. Let us see how to solve this problem. It is given in the question that a conducting sphere of radius capital R equals to 1 meter is placed in air. The breakdown electric field in air is mod of E vector equals to 3 times 10 to the power 6 volt per meter. The permittivity in the vacuum epsilon naught is 8.85 10 to the power minus 12 farad per meter, and the electronic charge is 1.6 times 10 to the power minus 19 coulomb. Now we know the electric field on the surface of a conductor is given by E equals to sigma by epsilon naught, where sigma equals to charge density on the conductor surface. Now, if n is the number of electrons on the surface of conductor, then sigma is given by n times E divided by 4 pi r square. So, this is the surface area of the conducting sphere. Hence, the electric field on the surface is Ne divided by 4 pi r square times epsilon naught. To avoid the breakdown, the maximum number of electrons that can be put on the sphere is n equals to 7 into 10 to the power n. Here we have to find the n, and the corresponding breakdown electric field mod of E that is given in the question is 3 times 10 to the power 6 volt per meter. So we will put all the values in this equation. So our maximum value of E is 3 times 10 to the power 6, that is equal to n times E. So 7 into 10 to the power n times 1.6 times 10 to the power minus 19 divided by 4 pi r square epsilon naught. So 4 pi times 1 square, because r equals to 1, the radius equals to 1, times the permittivity in vacuum, that is 8.85 times 10 to the power minus 12. So we have 10 to the power n equals to 3 times 10 to the power 6 times 4 pi times 1 square times 8.85 times 10 to the power minus 12 divided by 7 times 1.6 times 10 to the power minus 19. If we calculate this, we will get approximately 10 to the power n equals to 3 times 10 to the power 14. So n equals to log of 3 times 10 to the power 14. This will give approximately 14.47. So the value of n in the integer form is 14. Although the value must lie in between 14 to 15. If you get the answer 14 or 15, that is also correct. So according to our solution, the maximum number of electrons that can be put on the sphere to avoid electrical breakdown is about 7 times 10 to the power 14. So the n value is here 14. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 2 marks, and the topic of the question is electromagnetism. The question is, a charge Q moving with uniform speed enters a cylindrical region in free space at t equals to 0 and exits the region at t equals to tau according to the figure. Which one of the following options best describes the time dependence of total electric flux phi is a function of t through the entire surface of the cylinder? So there are 4 options given. We have to choose the correct options which describes the graphical plot of phi as a function of t in a proper manner. So let us see how to solve this problem. So it is given that a charge q moving with uniform speed enters the cylindrical region in free space at t equals to 0 and exits the region at t equals to tau. So this is our cylinder. So we are dividing the region into 3 parts. So region 1, region 2 and region 3. So charge is initially at region 1 in the free space. So it is coming towards the cylindrical region and it enters through this surface of the cylinder and it enters the region 2. Then it travels through the cylinder for the time interval t equals to tau. Then again it exits and enters the region 3, which is free space. So we have to find the time dependence of total electric flux as if phi as a function of t through the surface of the cylinder. So that's the surface of the region 2. Now we'll consider the Gaussian surface for this problem same as the cylindrical surface. When the charge q is inside the cylindrical Gaussian surface, that is in the region 2, according to the Gauss law of electric flux, the electric flux is equals to charge enclosed by this cylindrical Gaussian surface divided by epsilon naught, where epsilon naught is the permittivity of free space. Now, in this case, this q enclosed, that is charge enclosed by this cylindrical Gaussian surface, is time dependent. Because this charge is moving, so the charge is inside the cylindrical Gaussian surface for the time interval 0 to tau. So our q enclosed is equals to q for this time interval 0 to tau, otherwise it will be 0 in region 2. So the time dependent electric flux will be q enclosed by epsilon naught, that is q by epsilon naught for the time interval 0 to tau and 0 in otherwise. So the plot for the electric flux phi as a function of t, it will be looking like this. So our electric flux is constant, that is q by epsilon naught for the time interval 0 to tau, and it will be 0 after t equals to tau. So it will be option D, that is the correct option for this question. So we have discussed this problem and we found that option D is the correct answer for this question. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and the topic of the question is electromagnetic theory. The question is, a plane electromagnetic wave of wavelength lambda is incident on a circular loop of conducting wire. The loop radius is small a, where small a is very less than the wavelength lambda. The angle in degrees made by the Poynting vector with the normal to the plane of the loop to generate a maximum induced electrical signal is. So we have to find the angle made by the Poynting vector with the normal of the plane of the loop to generate a maximum induced EMF. Let us see how to solve this problem. Let us consider a small loop having radius small a lying in the xy plane. The normal to the plane of the loop is along z direction, and that is denoted by n cap. Now the magnetic field vector, that is B vector, of the incident EMF on the loop is making an angle theta with the normal to the plane of loop. According to the Faraday's law of electromagnetic induction, the induced EMF is given by E equals to minus d phi b dt, where phi b is the magnetic flux, that is denoted by surface integral of the magnetic field vector, that is B vector. So induced EMF E is equals to minus d dt of surface integral of the magnetic field vector, that is B. We can write this induced EMF as E equals to minus of surface integral del B del T dot product with the elementary surface vector, that is ds vector. Now n cap vector is along the ds vector, so we can write it as minus of surface integral of del B del T dot product with n cap times ds. So if we just write this dot product in terms of the magnitude of these two vector and angle between them, then we can write it as E equals to minus of surface integral del B del T ds cos theta, where theta is the angle between this V vector and n cap vector. Now if we have seen the expression for the induced EMF generated by the EM wave on a loop, then we can see to generate the maximum induced electrical signal, that is EMF, the angle theta should be 0 degree. That means the magnetic field should be parallel to the in cap, or 180 degree, that is the magnetic field is anti-parallel to the in cap, so that the magnitude of the uh, induced EMF will be maximized. Then in that case cos theta will be either 1 or -1. Now if the magnetic field vector B is along parallel or antiparallel direction with the normal to the plane of the loop, the electric field vector of the EM wave will be in the xy plane, that is in the plane of the loop, since the electric field vector and magnetic field vector is mutually perpendicular for a TEM wave, that is transverse electromagnetic wave. So till now what we have seen, our magnetic field vector is along the or antiparallel to the normal to the plane of loop, and the electric field vector will be in the plane of the loop. Now Poynting vector for an EM wave is given by S vector equals to 1 by mu naught times E cross B. Now if we consider the magnetic field vector is along n cap direction and our electric field vector in the xy plane, then E cross B will also be in the xy plane, and that will be same case if our magnetic field vector is antiparallel to the n cap direction. So S vector will be in the xy plane, that is in the plane of the loop. Hence S vector will make 90 degree with the normal to the plane of the loop to generate a maximum induced EMF. So we have solved this problem and we found that the angle in degrees made by the Poynting vector in the normal to the plane of the loop to generate a maximum induced electrical signal, that is induced EMF, is 90 degree. This question is from the GATE Physics paper 2020. This is a numerical answer type question having 2 marks. The topic of the question is electromagnetic theory. The question is, a sinusoidal voltage of the form V as a function of time t equals to V0 times cosine of omega t is applied across a parallel plate capacitor placed in a vacuum. Ignoring the edge effects, the induced EMF within the region between capacitor plates can be expressed as a power series in omega. The lowest non-vanishing exponent in omega is. So let us see how to solve this problem. It is given that a sinusoidal voltage of the form V as a function of time t equals to V0 times cos omega t is applied across a parallel plate capacitor. Let the separation between capacitor plates be small d. So it is shown in the schematics that two plates of the capacitors are separated by the small distance small d, and we have considered a small circular loop at the center having radius small r, and the area of the loop is given by the shaded region here. So we will calculate the induced EMF along this circular loop. So the electric field between the plates of the capacitor is E equals to the applied voltage along the capacitor plates, that is V as a function of small t, divided by the separation of the capacitor plates, that is small d. So the time varying electric field between the capacitor plates is given by E as a function of small t equals to V0 divided by d times cos omega t. We know that according to the Maxwell's theory of electromagnetic induction, if a time varying electric field exists in a region, then there will be a time varying magnetic field associated with that time varying electric field, and that is given by the Maxwell's equation. Curl of the magnetic field B equals to mu naught times epsilon naught times daily del T, where mu naught is the magnetic permeability in the vacuum, epsilon naught is the electrical permittivity in the vacuum, and E vector is the electric field vector that is coming here due to the applied time varying voltage across the capacitor plate. Now we will take the surface integral both sides of this equation. So it is given by surface integral of the curl of B vector equals to mu naught epsilon naught times surface integral of daily del T. Here the surface is considered by the surface area of the small loop of radius smaller that has been shown in the schematic in the first slide. Now we can convert this surface integral into the closed path integral. So that is given by closed path integral, line integral of the B vector equals to mu naught times epsilon naught times surface integral of daily del T times the ds vector. So here the line integral part will give B times 2 pi r. Here 2 pi r is the circumference of the small loop having radius smaller that we have considered in the first slide, and that is equal to mu naught times epsilon naught times this daily del T, that will give minus v naught omega divided by small d times sin omega t times the surface area of the circular loop, that is pi r square. So from this we can find the associated magnetic field, that is B equals to minus R times mu naught times epsilon naught times V naught divided by 2 small d times omega times sin omega t. So this is the expression for the time varying magnetic field associated with the time varying electric field between the capacitor plate. Now, according to the Faraday's law of electromagnetic induction, we know that if a time varying magnetic flux exists in a region, then there will be a induced electromotive force, and that is given by induced EMF E equals to minus d phi dt. Here phi is the time varying magnetic flux in the region. So the induced EMF E equals to minus d dt of the magnetic flux that is given by magnetic field B as a function of time times the area of the region. So A is the area within the region between the capacitor plates here. Now area is constant here, so it can come out from the derivative. So E equals to minus A times d dt of the magnetic field. Now we have calculated the magnetic field associated with the applied voltage across the capacitor in the last slide. So this d dt of B will give here as E equals to A times, that is the area, times R mu naught epsilon naught V naught divided by 2t times omega square cos omega t. Now the terms in the parenthesis are independent of omega, so we will not write it again and again. We will consider the omega dependent part here. Now we will expand this cos omega t in the power series. So this expression will give E equals to this term times omega square times the power series of the cosine of omega t, that is 1 minus omega t whole square by 2 factorial plus omega t to the power 4 by 4 factorial plus so on. Now we will multiply omega square with this series, so this will give omega square minus omega to the power 4 t square divided by 2 factorial plus omega to the power 6 times t to the power 4 by 4 factorial plus so on. So we can see the lowest non-vanishing exponent of omega is 2. Therefore, the lowest non-vanishing exponent in omega from this expression is coming out to be 2 here. According to our solution, the lowest non-vanishing exponent in omega is 2.